Hello everyone and welcome to this new video where I will be sharing what I learned regarding transformers, not transformers. So today we're deconstructing the architecture that changed everything, the transformer. As illustrated here, the fundamental shift in AI was moving from the sequential processing of recurrent neural networks to the parallel attention mechanism of transformers. So this is the RNN architecture, this is the transformers. Before 2017, models processed language like a human reading in a single line, step by step. The transformer proposed in the paper Attention is All You Need abandoned this entirely. Instead of sequence, it processes the entire sentence at once, creating a dense web of connections where every word looks at every other word simultaneously to understand the context. So, to understand the solution, we must understand first the problem with the old architecture. In RNNs, information moves through time, so T1, 2, 3, 4. If we process the black cat 8, the model must memorize V at step 1 and carry that memory all the way to step 4. So this created two major issues. As the sequence gets longer, the memory fades. By the time the model predicts the last word, the context from the beginning is often lost or diluted. So we cannot use the full power of GPUs because we must wait for step 1 to go to step 2. We must wait for step 2 to finish, to 3, to 4, etc. This serial nature prevents parallelization, making the training on large datasets incredibly slow. So the transformer solves this by dispensing with the recurrent entirely, as you can see in the diagram. Instead of a timeline, we have a block where every input word is connected to every other word instantly. This allows for two things. The distance between V and 8, for example, becomes irrelevant. They are just one operation apart, allowing the model to draw dependencies regardless of the distance. And because there is no time step loop, we can feed the entire sentence into the model at once, utilizing like massive parallel computing power to train on datasets as large as the internet. That's why it's called LLMs, or large language models. The L stands for large. So now let's look at how the model actually handles text. It happens in 4 stages. The first one is tokenization. We break the word into number IDs. Here we will assume that each word is a token for simplicity, but in the real world it's not. A token can be, for example, the first 2 letters, and then the next token could be this. So E space BLA is a token. It depends. We will see a whole video on tokenization. And then we convert those IDs into a vector's list of numbers that capture meaning using embeddings. So like similar words like cat and dog should be close to each other. If we have the words orange, this is an O, and apple, they should be close to each other but far away from the animals. We saw embeddings, and then because the model of transformer reads all the words simultaneously in parallel, it has no inherent concept of order, so it doesn't know that black came before cat or cat came before T. So it doesn't know the order. To fix this, we inject positional encoding. So vectors using like, for example, wave patterns like cosines into the embeddings. There are many other techniques that we will see in a separate video. This adds a unique signal to each word based on its position, allowing the model to distinguish the order. So it's like we're adding another vector that makes us learn the position of every word or every previous vector that represents the word or token. So this brings us to the core mechanism, the self-attention. Static embeddings aren't enough because words change meaning on the context. We look at this example. The animal didn't cross the street because it was too tired. What does it refers to in this context? The animal, we know that, but how can the model know? For example, if we change tired to white, it now refers to the street, not the animal. So self-attention allows the word it to look at all other words in the sentence. If the context is, for example, tired, the model calculates like a strong gravitational pull towards animal. So if it was between animal and street, if the context was too tired, we should get closer to animal, but if it was white, closer to the street. Mathematically, to achieve this, we use 3 vectors for every word: a query Q, a key, and a value. Think of a database or a library search. The query asks what are you looking for, the key, the label, or the index you match against, and the value is the actual content. To calculate attention, we take the dot product of the query and key. A high dot product means they are similar, or we give them a high score. And then we run those through a softmax function, which is this one. We can standardize them or scale them using many different techniques. This is one of them, the square root of the dimension of the keys. And then we do the softmax, as we said, that would turn them into probabilities. So percentages that sum to 1. And then we multiply them by the value. We will see the mask option later on. And then, as we said, multiply by the value to get the final context-aware representation. That was just one attention head, but in practice, just one isn't enough to capture the complexity of language. We use multi-head attention, which runs several attention layers in parallel, as shown in this color-coded diagram. Like different heads focus on different relationships simultaneously. For example, this red head might focus on adjectives modifying nouns like black, cat. This one might focus on the subject-verb relationship, for example, the cat ate. And by concatenating all these heads, the model builds a rich understanding of grammar, like logic and tone, all at once. So after the attention mechanism, the data moves through the rest of the encoder block. For the residual connection, we add the original input back to the output. This creates a highway for information, preventing the original identity of the word from being lost and solving the vanishing gradient problem. Of course, we do normalization, and then we pass to the feed-forward network. While attention like gathers the context, this layer processes it. It applies nonlinear transformation to each word independently to learn the complex pattern. This block, the attention plus the feed-forward network, is repeated 6 times in the original paper, our original architecture. Now we move to the decoder. Now we will see the masked that we said that we will see this part. The decoder site, which generates the output. For example, translation from English to French or any other language. So during training, we must prevent the model from cheating by looking at future words. For example, this is what we call masked infinity. If we have, like, this is the French translation of the black cat, le chat noir. So once we're in this phase, we prevent it from seeing the future words. Now that we predict the second one, we prevent them from seeing the next word or token. How do we do this mathematically? Is by setting the attention scores for future positions to negative infinity. So once they passed through the softmax activation function, they would turn into 0, effectively blinding the model to the future and forcing it to predict based on only the past context, because the softmax of minus infinity is 0. Okay, now this is the bridge between understanding and generation, the encoder decoder attention. Here the query comes from the decoder. For example, I have generated le and I need a noun. The keys and the values come from the encoder to complete the complete understanding of the English sentence. For example, the black cat. This allows the decoder to focus on the specific part of the English input that is relevant right now, focusing on cat to generate sha, bridging the two languages. Now when we use the model to generate text or inference, it works in an autoregressive loop, unlike the encoder, which processes everything at once. The decoder generates one word at a time. So start by the special token as the first input, SOS or start of sentence. So feeding this into this block should give us le as output. We use it as an input. We predict the next word, and then we do the same until finally we predict EOS token or end of sentence. Once the model predicts EOS, it knows that we finished this task, or the translation, or generation, or any other task. So how is the final word chosen? The decoder outputs a vector of numbers. We pass this through the linear layer to expand it into the size of the entire vocabulary, for example 30,000 words. Then the softmax function converts these numbers into probabilities in the bar charts here. This word has 85% probability, while this one is 10 and this one is 5. We usually select the word with the highest probability. This is what we call greedy search, or we can use beam search to consider multiple future paths. So we take these two into consideration. This brings us to the full architecture. This is a very famous figure from the paper, with a stack of 6 layers in the encoder that processes the input into the deep contextual representation, here using the embedding, tokenization, positional encoding. We go to the multi-head attention, normalize them, going to the feed forward, again normalizing again. And here on this right part, also 6 layers of using masked attention and cross attention to generate the output. This unified structure, relying solely on attention, allowed for the massive performance jumps that we see in the modern AI era. This is a critical part. It is because it is critical to distinguish between how the model is trained against how it is used. In the training, we use teacher forcing. We feed the input and the target output simultaneously. Because of masking, we can calculate the error of every single word position at the same time. This is fully parallel and extremely fast. And in the inference or generation, this is sequential. We generate one token, append it, and repeat. This is why tools like ChatGPT generate text one word at a time. Why this matter? This architecture is the foundation of the modern generative AI revolution. Like the T in ChatGPT stands for transformer. By replacing recurrent loops with parallelizable matrices, this architecture enables us to scale from small datasets to reading the entire internet. So from the original paper to BERT, GPT-1, 2, 3, 4, now we have 5, Claude, Gemini. The transformer remains the engine driving these capabilities. So that was it. Thank you for watching. Please like and subscribe to the video.